Hello, this is the next video in a playlist that I'm calling hypothesis testing, and we're in the unbiased hypothesis testing phase, and we're looking at uniformly most powerful unbiased two-sided composite versus composite tests, and we're in the binomial setting. And so the previous video has that as a title, and this one is just using R to help us find those critical regions or the bounds. And the test is the true proportion between two values, say P1 and P2, or is it outside of those two values? And this is it. And so first I always like to remove all the objects from the list. And we're going to assume P1 is 0.25 and P2 is 0.45. We're going to have an alpha of 0.05, a sample size of 25. And then I create all possible C1 and C2s. That's what that expand grid does. But we have to make sure that C1 is strictly less than C2. So that's what that command does. So we just removed a large, or half of the, or actually more than half of the matrix there. Then this K1, K2, K3 that I'm getting ready to calculate, in the previous video we created sort of a two equations, two unknowns, and we had constants. And that's what these K1s are. We're calculating those sort of constants given C1 and C2. These are the constants. And then we solve for gamma 1, plug it into gamma 2, or the equation. We solve for gamma 2, then we use gamma 2 to solve for gamma 1. Now we have lots of these, lots of rows still, but we can only keep the gamma 1s and gamma 2s that are between 0 and 1 because it's a test function. And then that just created unique bounds for this test. And first of all, I want to see if each tail has a 0.05 cutoff value. That's what these are doing. They're calculating the probability of being in the tail. And it is. That's what these two values here, left tail, right tail. The cutoff is 3 and 15. Gamma 1 and gamma 2 are here. And that's it. Let's look at the power curve and plot them. And so this is the power curve. The null is that we're between 0.25 and 0.45, and notice that the power curve is below the alpha 0.05 level. That's the horizontal line. And notice the power curve is above alpha in the alternative region. That's what makes it an unbiased test, and it is uniformly most powerful. So let's do a computer simulation in this. We store the cutoff values C1 and C2 in their own variable. Same way with gamma 1 and gamma 2. We do 1 million loops, the replications. So we generate a binomial of that size, and then we see where it falls in the rejection region. That's what this does. Let's table it, and there's how many trues and false, meaning was it in the rejection region or not. And let's just look at the power divided by how many simulations we did, which is 1 million. And we have a power of 0.44, simulated power of 0.44. Let's plot that on the power curve and see where it falls. So in our simulation we assume that the true proportion is 0.6, and we simulated a 44%, and look at that, it's right on the curve. And with a million replications, I'd be more surprised if it wasn't pretty much on that curve. So it agrees with the theoretical power. Now I have a leave out one tail approach where we just ignore it. Like when we assume that P1 is true, we calculate the probability of being in the left tail, ignoring the right tail. And then when P2 is, we assume it's true, we calculate the probability in the right tail and ignore the left tail. And it makes it really, really easy to find the critical regions. And here you just use Q binom to find them. And then you can solve for gamma. I'm going to have gamma 1 and gamma 2. I'm going to have to point you back to the video where we solve for gamma 1 and gamma 2. And let's test to see what the critical region would be using this leave out one tail test. and it's 0.05006298. So it agrees with an alpha level test up to 1, 2, 3, 4, 5, 4 or 5 decimals. That's pretty close. Now let's calculate um, the alpha level, the true alpha level, and if you round it, it's exactly 0.05. I mean, it's crazy. So under the one-tailed approach, the C1 and C2s are the same, 3 and 15, but the gammas are a little different. But look how close they agree: 0.279, 0.278, 11.6, 11.25. So it's a pretty approximately uniformly most powerful test, unbiased, and you don't need a computer to calculate the critical region. So let's create the power function for this leave out one tail test, and let's look at the power curves. I plotted them on top of each other, and it just looks like a red line. On my screen I can tell there's like little brief black dots, sprinkled throughout, so they're not exact, but they are so close. I mean, they're accurate to 4 decimals. Of course, it's going to look right on top of each other. Now, in previous videos, I've zoomed in and tried to show you that they're technically not the same, but I'm going to leave that to you if you want to do it. And as with all my videos where I use R code, I copy and paste the code into the comments, and then I try to pin it so it always stays at the top. And that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.